Here is the big result regarding uniform continuity that we want you to know. So let's let X be our domain, and let's assume that our domain is closed and bounded. And let's let f be a function whose domain is X, range is the reals, and we're going to assume that f is continuous. And the conclusion is that every continuous function on a closed and bounded set is also uniformly continuous. Something like 1 over x, that can only work on our non-closed interval, our open interval from 0 to infinity. And here is how we go about proving this. So f is uniformly continuous. Let's write down the definition again. If for all positive numbers epsilon, we have that there exists a positive number delta greater than 0 such that, let's put this in for all language, for all x, y in our domain X with distance from X to Y being less than delta, we have that f of X minus f of Y is less than epsilon. And what we're going to do is we're going to prove the contrapositive. That is, we're going to suppose that f is not uniformly continuous and prove that it is not regular continuous. So let's suppose f is not uniformly continuous. And then to not be uniformly continuous, we go through, we flip for all, we go through, and then that means that then for all epsilon turns into there exists at least one positive number epsilon such that, and then our for all delta flips into or there exists a delta, it flips into a for all delta. And then our for all x and y turn it into a there exist numbers x, y in our domain X with x minus y less than delta and f of x minus f of y not less than epsilon greater than or equal to epsilon. Okay, so now what are we going to do with this? What we're going to do is we're going to pick some such epsilon. Then we're not going to use all delta. We're only going to use some very specific deltas. Then for each natural number n, we have that there exist numbers x, y, both in x, that are x minus y. That's less than, we're using 1 over n as delta. So x minus y are within 1 over n of each other. And the other thing we need is that f of x minus f of y, that is at least epsilon. And now we're going to use this for all natural numbers n, so let's label them. Let's let them be xn, yn are the ones that are within 1 over n of each other, and then f of xn minus f of yn is greater than or equal to epsilon. So let's look at our sequence of xn's first. So this is giving us a sequence of points. So the xn's are in x. So, and x is bounded. So this is a bounded sequence. So by the Bolzano-Weierstrass theorem, there is a subsequence and the subsequence converges. And let's go ahead and name the thing it converges. We're going to call it x, and then our x and k's are converging to x. Now, our domain is closed. And our sequence, and therefore our subsequence, these, remember, were all points in x, and they're converging to the point x. So a closed set means that if you've got a sequence in a closed set, the limit's also in the closed set. So our limit point little x is in our domain little x, big X, and it should be pretty clear. And now let's suppose if f of x sub n sub k, that's a sequence, if that does not converge to f of x, then remember the definition of convergence is f maps convergent sequences to convergent sequences. Then f is not continuous at x, and we are done. Our goal is to show that our function f is not continuous, meaning not continuous everywhere on its domain. We're going to end up showing that it's not continuous at this particular target point x. So if f of x and k does not converge to f of x, then we are done. Otherwise, So suppose we are going to suppose f of x sub n sub k does converge to f of x. All right. Now we're going to need to show two things. The first is that the y and k's converge to the same point, and the f of y and k's do not converge to f of x. So let's start with the first thing. Y sub n sub k minus x sub minus our target point x. By the triangle inequality, that's at most y n k minus x n k, and then x n k minus x. Then y n k minus x n k, that's at most 1 over n sub k. And the NKs are increasing. It's a straightforward induction argument. This is at most 1 over k plus xnk minus x. And then it's a straightforward epsilon n argument that ynk goes to x. So you pick, I guess we're using epsilon for something. We're going to pick an eta greater than 0. Let n be such that if k is greater than n, then xnk minus x is less than eta over 2. Because xnk is converging to x, we can require this. And then standard trick, we're going to also require that n be bigger than 2 over eta. By the Archimedean principle, there's an integer that's bigger than 2 over eta. You just take the bigger of the integer you get from the definition of convergence and the integer you get from the Archimedean property. And then the conclusion is that if k is bigger than n, then ynk minus x is less than eta. So the conclusion is that ynk is indeed converging to x. Now let's recall that we assumed, we are now in the case, we assumed that f of x sub n sub k is converging to f of x. So let's let m be a natural number, be such that if, let's see, little k is bigger than m, then f of xnk minus f of x is bigger than epsilon, is less than epsilon over 2. Remember, epsilon is the number we picked at the start. It's the number where f of xn, and this f of xnk minus f of x, f of ynk, that thing is always at least epsilon. So f of ynk minus f of x, by the reverse triangle inequality, that's at least f of ynk minus f of xnk. Then you subtract off f of xnk minus f of x. And notice that this is at least epsilon over 2. So eventually you get that f of y(n)k minus f of x is bigger than epsilon over 2. There, you are never going to get an integer or you get past that and you get f of y(n)k minus f of x less than epsilon over 2. So f of y(n)k does not converge to f of x, but y(n)k does converge to x. So f is not continuous at our limit at point x. And that completes the proof. The last thing we're going to talk about in section 1.7, and in fact the last thing we're going to talk about in chapter 1, this is actually a topic that your book thinks belongs in section 2.3, so pretty far into chapter 2, but I think there are a few theorems from there that it makes more sense to talk about now. So we're going to start discussing at this point what are called monotone functions. So here is our definition. So let's let x be a domain in the real numbers and f be a function from x to r. And then we're going to write down several definitions. If f of x is less than or equal to f of y for all x, y in x with x less than y, if making the input bigger always is never makes the output smaller, either keeps the output the same or makes it bigger, we say that f is an increasing function. And if we have strict inequality, making the input bigger or always makes the output bigger. Then we say f is strictly increasing. There is decreasing and strictly decreasing functions too. I think I will not write down the precise definitions. They're pretty straightforward. You just flip the inequality f of x is greater than and f of y, f of x is greater than or equal to f of y. So let's say, but there is one word I want to mention. If f is increasing on all of x, so it is either increasing on all of x or decreasing on all of x. The term for that is, we say f is monotonic, because there are a lot of theorems that are true about both increasing functions and decreasing functions, so it makes our life a bit easier if we can have one word for that means either increasing or decreasing. And notice that monotonic means something that's increasing everywhere, so something like that, or a function that's decreasing everywhere, something like that. But something like a sine wave, we see it's increasing for a while and then starts decreasing and then goes back to increasing. This does not count as monotonic. To be monotonic, you have to be increasing everywhere or decreasing everywhere. You can't be increasing for a while and then decreasing for a while. You can't switch back and forth. And here is the big result I want to prove about monotonic functions, and specifically about continuous monotonic functions. So let's let I be an open interval. What we're about to prove actually works if I is any interval, but extending to closed or half-open intervals is just a little annoying, so I think I'm going to leave that as an exercise. And we're going to let f be a function whose domain is our interval I. And we're going to say f is continuous, which is why I think this proposition belongs in section 1.7, and also strictly monotonic. So strictly increasing or strictly decreasing. And then f is an invertible function. It has an inverse, and the inverse is continuous. And let me write out exactly what that means. Then there is a function g whose domain is f of I and whose range and we'll see image is I, such that we have that g is continuous and g and f are inverses, meaning that g of f of x equals x for all x in our interval I, and f of g of y is y for all y in f of I. And let me remind you that corollary 1.7.8 says because f is continuous, f of I is also going to be an interval. Which should clear up, which should make this look a bit more symmetric. All right, let's prove this. And as usual, we're going to pick one of the two cases. We're going to pick the strictly increasing case because the strictly decreasing case is very similar. So we're going to start by proving that f is 1-to-1. So let's suppose that x and z are in our domain, and that f of x is equal to f of z. And then f of x is not greater than f of z. So x is not greater than z. Writing this slightly more usually as x is less than or equal to z, because remember, in the real numbers, either you're greater than, less than, or equal to. And similarly, f of z is not greater than f of x, so z is not greater than x. Z is less than or equal to x, so z equals x. And thus f is 1-to-1, is injective. All right, now many of you already know that injective functions always have inverses, so I'm just going to quickly review that argument. So if y is in the image of our domain, then y is equal to f of x for some x in I. That's what image means, but we've just shown that f is injective, so y equals f of x for exactly 1x in our domain I. And now we are going to define the function g by g of y equals x. This is a well-defined function. If you give me a y and f of I, there is an x that works, and there's only one x that works. So that means that you know what g of y has to be, and there is, in fact, something it can't be. And then I'm going to notice f of g of y, that's equal to f of x, which by assumption is y. So that's one side of our, or showing that f and g are inverses of each other. They undo each other. Now, if conversely, if x is in I, then f of x is in f of I, which recall is the domain of g. So g of f of x exists, and g of f of x is the number you plug into f and get f of x. X is the number you plug into f and get f of x, so clearly g of f of x, that has to be just x. So now we want to show that g is continuous, and then we'll be done. So we are going to choose some y in our domain of g in our f of I, and then our goal, what we want to show is that g is continuous at y. And then here's how we're going to do it. We're going to let x equal g of y. So remember, that means that f of x is equal to y. And now we're going to pick an epsilon greater than 0 and we're going to show that G is continuous at Y using theorem 1.7.5, using the epsilon delta characterization of continuity. You can do this using the convergent series definition of continuity too, but it's more annoying, so we're going to use epsilons and deltas. And now I'd also like to use the fact that I is an open interval. You're going to work through what happens at the endpoints. That might be a homework or exam problem. So, since I is open, and X is in I, by proposition 1.6.4, there is a positive number. I can't call it epsilon or delta, so let's call it rho greater than 0, such that x minus rho, x plus rho is contained in I. And let's let x plus, this is going to be x plus whichever is smaller, epsilon over 2 and rho over 2. And we're going to let x minus be very similar. We're just going to subtract this epsilon or rho over 2. And then, what do we have that's true? Well, first off, epsilon and rho are both positive, so their minimum is positive. Divide by 2, they're still positive. So x is between x minus and x plus. So x minus is strictly less than x plus is strictly greater than x. And x plus is also strictly less than x plus epsilon. X minus is strictly greater than x minus epsilon. And also, x plus is less than x plus rho. They're between x minus rho and x plus rho. So we have that x minus and x plus, they are both in x minus rho, x plus rho, which is contained in our interval I. So that's very abstract. Why don't I give you a picture of what is going on? So here is our interval I. Here is our strictly increasing function. And then over here we have f of I. We grab our point y in I. That is g of x. And then we want to put epsilons on either side of x. So we pick our epsilon, we go a distance epsilon in either direction. And then we're going to grab our x minus here, our x plus here, and see what we get. And what we're going to get is that here is our f of x minus, and then up here is our f of x plus, And then you see anything between f of x minus and f of x plus is going, G is going to send it's somewhere or between x minus and x plus, and then so we'll get continuity. So let's write this out rigorously. Let's let delta be whichever is smaller. F of x plus minus f of x, and f of x minus f of x minus. And then notice two things. The first is that f is strictly increasing, f plus is strictly greater than x, so f of x plus minus f of x is positive. Same thing for f of x minus f of x minus. Notice that delta is. And now we want to use the epsilon delta definition of continuity. We want to show that for every epsilon, we've picked epsilon already, there exists a delta. It's this delta we've just found, such that if y minus z is less than delta, then we want to show that g of y minus g of z is less than epsilon. So let's suppose, so let's pick some z that is true for. So y minus z absolute value is less than delta. And then you can check z is between y minus delta, y plus delta. Y is the same as f of x, so we can write f of x minus is less than z is less than f of x plus. But because f and g are inverses, we can write z as f of g of z. And then if x minus was bigger than g of z, then f of x minus would be bigger than f of g of z because f is increasing. So we can say that f of x minus is not big. So we can say that x minus is certainly not bigger than g of z. X minus must be less than or equal to g of z, and they cannot in fact be equal to each other. If x minus was equal to g of z, then f of x minus would be equal to f of g of z. So in fact, we've got a strict inequality here. We've got another strict inequality, g of z is less than x plus, which we said was less than x plus epsilon. That's g of y plus epsilon. And on the other side, we've got a g of y minus epsilon. So we've got this long chain of inequalities. And we can write this as g of y minus g of z is less than epsilon. So we picked an epsilon, we found a delta such that if y minus z is less than delta, then if y minus g of z is less than epsilon. And so by theorem 1.7.5, G is continuous at y. And since y was arbitrary, that means that G has to be continuous at every point in I. So in particular, the function f of x, or maybe I should call it g of x, equals the cube root of x. That's the inverse function to x cubed, which we know is continuous because it's a polynomial. That is continuous on the image of x cubed. That's continuous on all of the real numbers. X squared is not strictly increasing on all the real numbers, but it's increasing on the positive numbers. So the square root of x is continuous on the interval from 0 to infinity. And notice that if we proved proposition 2.3.9 on enclosed intervals, we would be able to use that x squared is continuous and monotonic on the non-negative numbers, so we would know that the square root of x is continuous on this closed interval from 0 to infinity.